Welcome to the third lesson in Session 8 of the Rational Root Theorem. The Rational Root Theorem provides us with a list of possible rational roots to a polynomial equation. Once we generate the list of possible rational roots, we then use synthetic division to identify the actual roots of the polynomial equation. And to get started, we take a polynomial equation and we identify the factors of the constant term, which we call p, and we identify the factors of the leading coefficient we call Q. We then make a list of all the possible combinations of P over Q. That is the list of possible rational roots. Once we generate the list of possible rational roots, we're going to use synthetic division to identify which of the possible roots are actual roots. The rational root theorem does not give us any additional information about irrational or complex roots. We have a couple of examples, and what we're going to be asked to do here is to use the rational root theorem just to make a list of possible rational roots. In our first equation, we have 2x to the fourth minus 4x to the third plus 3x minus 8 equals 0. So the first thing we need to do is identify the values of p, which are all the factors of the constant term. So they represent the numbers plus and minus 1, plus and minus 2, plus and minus 4, and plus and minus 8. Those are all of the different factors of negative 8. Next, we identify the factors of the leading coefficient, which is our value of q. So the values of q are just plus and minus 1 and plus and minus 2. Those are all the combinations, those are all the factors that divide 2. Now I take all of the different combinations of p over q. So if you notice, we're going to take 1 over 1. So plus and minus 1 is a possible root. 1 over 2, so 1/2 is a possible root. And we move down, we have 2 over 1, so 2 is a possible root. 2 over 2 is 1, and we already have that listed, so we don't need to list it again. Then we have 4 over 1, which is plus and minus 4. 4 over 2 is 2, which we already have listed. We have 8 over 1, which is 8. And we have 8 over 2, which is 4, which we already have in our list. So the complete list of possible rational roots is plus and minus 1/2, plus and minus 1, plus and minus 2, plus and minus 4, and plus and minus 8. So in this case, there are 2, 4, 6, 8, 10 possible rational roots to the polynomial equation that we started with. The next example, we're going to follow the same process. The equation we're given is 6x to the fourth minus 2x to the third plus 5x to the second plus x minus 10. We start by taking the factors of the constant. So the constant in this equation is negative 10. So all the numbers that evenly divide negative 10 include plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. The factors of the leading coefficient, I have a leading coefficient here of 6. The factors of the leading coefficient are plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. Now, with the increased number of factors, we're going to have a greater number of combinations of solutions. So when I take all the combinations of p over q, notice we have 1 over 1, 1 over 2, 1 over 3, 1 over 6, and then we move on. 2 over 1, 2 over 2 is already in our list, 2 over 3, and 2 over 6 simplifies to 1/3, so that's already in our list. So once we exhaust all those possibilities, the possible rational roots are plus and minus 1, plus and minus 2, plus and minus 5, plus and minus 10, plus and minus 1/2, I accidentally listed that twice, plus and minus 5 over 2, plus and minus 1/3, plus and minus 2/3, plus and minus 5/3, plus and minus 10/3, plus and minus 1/6, and plus and minus 5/6. So in this case, in the next example we have, we're going to determine what the actual rational roots are. So we have an equation, the function f of x is equal to x to the third minus 3x squared plus 7x minus 10. So we start by using the rational root theorem. That's going to give us the possible rational roots. And then we're going to use, in this case, we're going to use synthetic division to identify the actual rational roots. So we make a list of possible roots. So I take my values of p, which represent the factors of my constant, which is negative 10, and I take the factors of q, which is the factors of my leading coefficient, which is 1. So the list of possible roots, I've got 10 of them, plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Now I need to start and use synthetic division with each of the 10 possible solutions to identify the actual solutions. So if I use synthetic division on a value and I get a remainder of 0, that tells me that the root divides the equation evenly and is therefore a solution to the equation. So you see in our first example, we use negative 1. When I run negative 1 through using synthetic division, I end up with a remainder of 21. Since we have a remainder, negative 1 is not a solution. So I move on, and I try positive 1. And you see the same thing happens. When I use positive 1, I end up with a remainder of 15. So positive 1 is not a solution. I tried negative 2. Still, I got a remainder of negative 44. Finally, when I use positive 2, I end up with my first rational root. So when I run positive 2 through my equation, I end up with a remainder of 0. That tells me that 2 is a rational root to the function. Moving on, I got to try 5. And negative 5, I do not get remainders of 0. And I try negative 10 and positive 10, and again, I do not get remainders of 0. So we knew from a previous lesson with a third degree function, the fundamental theorem of algebra tells me I'm going to have one real solution or I'm going to have 3 real solutions. So now I have one rational root, so the other 2 roots are either irrational or they're complex. 2 is the only rational root of this function. Okay, our next example, we have f of x equals 6x to the 4th plus 35x to the 3rd minus x squared minus 7x minus 1. So I got to make my list of possible roots. So I take the factors of p, which is negative 1, and I take the factors of q, which is 6. Make the combinations of p over q, I get plus or minus 1, plus or minus 1/2, plus or minus 1/3, and plus or minus 1/6. So I've got 8 different possible rational roots to test. So I'm going to use synthetic division with each of the 8 possibilities to identify which of the possible roots are actual solutions. Using negative 1, I get a remainder of negative 24. Using positive 1, I got a remainder of 32. Using negative 1/2, I got a decimal remainder, 6.75. Once decimals get introduced, you're not going to get away from them. So once you notice that you start working with decimals, and when you're using synthetic division, you can pretty much eliminate that solution from contention. So once you end up with negative 15.5 here, you know negative 1/2 is not going to work. Moving on, we try positive 1/2, and here, lo and behold, we've got a solution. So we got a remainder of 0 when we tested 1/2. So 1/2 is a solution to my function. All right, now there's 4 more solutions. They may be complex. I may have some irrational roots, but I should expect to find at least one more rational root. And negative 1/3 produces that rational root. So running negative 1/3 gives me a 0 as a remainder. Now there could be 2 more, or that could be it. When I test positive 1/3, you see we end up with a decimal. No need to go any further, so we dump and eliminate 1/3 as a possibility. Same thing occurs with negative 1/6. Once a decimal gets introduced, we can eliminate that, and the same thing with positive 1/6. So we have 1/2 and negative 1/3 as our rational roots. There are 2 more solutions to the function according to the fundamental theorem of algebra, and they could either be complex or they can be irrational. You can graph to find out that answer, but this is all we're asked to do in this problem. And that wraps up our lesson for the rational root theorem. Good luck on the test, and email us if you have any questions.